No, but then -1 you are going to multiply the intensity. No, but that's not allowed in median. It's called an order statistics filter. You can only order pixels. You cannot multiply. You cannot do averaging. Then it's like any other filter. So it has to be with an order. By ordering, you have to get it, not by any other means. All right. So let's go and talk about what is called edge detection. Okay, well, what we've been doing, I mean, many of those things will now be useful for that. And by the way, right, when we say edge, right, it does not necessarily mean that you're referring to a line or something. Okay, edge could mean a pixel, a place where there is a drastic intensity variation. Okay, and then right, eventually you could probably club them all together in order to make some interpretations that there is a line here, there is a curve there, things like that. But right now, right now it's not even clear as to when do I declare something as an edge pixel, and so on, right? But many of the things that we have done till now will now be handy. Okay, and that's what we mean. And no, okay, when does an edge even, okay, first of all, the applications, right? Why would you even want to do an edge detection? Applications are many, right? One of the things that we already saw, for example, even in CNN filters, when we said that the initial filters represent something that the visual system does, in the sense that, right, it actually picks up all the edges. You have regions that are sensitive to orientation of edges and so on, and then something else happens, right? Along the way, they get grouped, and then there's some nonlinear action on them and so on. So we have already seen that the low level features are important, and typical low level features are edges. But then there are several real life examples where we know that somebody just draws an edge map or somebody, then we know that there is still so much information even in edges, right? You can't say no to that, right? I give you an image, it doesn't mean that I have to shade every little part out there in order to convey something to you. Even without shading, if I just gave you a contour of something, right, you will still be able to, for example, a table, right? Do I have to tell all the gray levels there to tell you that it's a table? You don't need that, right? If you just draw the outline, you tell it's a table. Right, so that way edges are very important. I mean, right, and it's a matter of how you combine with them with maybe other information, or whether you take them as a standalone and proceed. That and all, right? We are not entering into. You could be doing that also, right? And then the other thing, right, that is the other thing, right, that you can ask is when does it arise, right? So when do you think that edges even arise? When do you see edges? I mean, you take an image, right? You see an possibly, right, looks like an edge, right? So when do you call that as an edge? Well, in the sense that so what I'm asking is that under what situations, right, can an edge arise physically? When can it arise? I mean, if there is, let's say, a shadow, perhaps, right, you will see an edge. If there is a color texture change, right, in an image you see an edge, right? So an edge, right, does not kind of does not always mean that there has to be a discontinuity in depth. Okay, without a discontinuity in depth also you can have edge variation. If there is a discontinuity in depth, very likely that you will have an edge there, but it doesn't automatically mean that it has to be there. So you can have various situations. For example, right, you can have, I mean, I think some examples are here itself which I can show. Okay, for example, right here itself, okay, if you go by, where is that full thing? So if you see here, right, I mean, okay, yeah, right, I mean, a definition is more or less like, where there is a significant change in intensity or transition. So you can have an artist line drawing, and then some of the things that I already talked about, right? So, and of course, there are also other things, using edges, right, you can actually, you can trace what is called a vanishing point in an image and so on. This, when we do single view geometry, right, we will come there, because you have seen these railway tracks and all, right, in an image, it will appear like they are meeting somewhere in the image, whereas in a real world we know that, right, they don't, right, but in an image, right, they seem to meet. So the point, right, where they seem to meet is called the vanishing point, and using that you can do certain things. So that is again based upon edges, right, that we can actually track them. Then, yeah, right, this is what I was telling. So there is something called a normal, this one a discontinuity, surface normal. A surface normal, which basically means that you could have an object, and then if the surface normal of the object suddenly changes because the shape of the object changes, you can get a discontinuity. You can get an edge. You can get an edge if there is a depth discontinuity. That means there's totally like you're moving from one object to another. Something is behind, something is in the front. This is a different object. That's a different object, but they are both coming in the same image. You will again see an edge. For example, what you are seeing here, right? This is like an edge. You can get an edge. I think, okay, now the color thing, I don't know, right, that seems to be missing here, but then, yeah, right, you can also get, if there is a texture, or maybe even here, I think you can see that here. For example, right, I mean, that portion where there is a shadow, right, I mean, there it looks like there is an edge. You can also have edges when there is a color change, texture change, so many, right, times when it arises. Now let's just go back and kind of, okay, and then, right, let's just go back and talk about some things, right, what we call, so two things that we typically use, what is called a gradient, okay, edge gradient. What is called an edge gradient. So by which, for example, right, what we mean is you could have, let's say, an image G, right, which is, let's say, xy, and we can have a gx, right, which is supposed to be telling how does the intensity vary along as I move along the x direction, right, which is a gradient. So right, this you can think of dou g, right, with respect to dou x. So this is like the change in intensity along this x direction. Then you can have something like gy, right, which is a gradient along y, that is dou g by dou y, right. And typically, right, what we are actually interested in is actually the magnitude of the gradient. So for example, right, so we can, so the magnitude of let's say gradient. So right, let me just write this as magnitude of the gradient of g, and that, right, I can write this as gx square plus, right, gy square root. And there is something else which is like the, right, orientation. Okay, so you can actually write something like, a direction, or see, right, orientation of the edge. Okay, by which, right, what we actually mean is, I'll just right, tell that in a minute. So direction of the edge. So this is like some, see, theta, it is equal to inverse tan of gy by gx. Okay, and what this actually means is this. See, for example, if we take our sort of, a convention to be this as increasing x, I mean x that way and then y this way, then what it means is, right, you could have, so for example, right, I mean, I could have an edge like this, right, where I have 0 to see 255. So what this means is I have actually a vertical edge, and then this you see theta, right, it points in the, it's a direction of, direction of the highest change in intensity, intensity. So for example, right, in this case you will have actually a theta which is actually 0 degrees, because along y, right, you don't have a variation at all. So it's like gy is 0. I mean, because the edges, right, there's only a transition along x, right, as you move. Along y, it's all 0 or it's all 255. So you have a gy which is 0, and then you have a gx, right, and therefore it, theta is 0. So if you change if you make it to be 255 0, then it will mean that the edge goes in the other way. Okay, so if you make this as 255 and you make this as 0, then your see theta will be this, which will be actually 180 kind of say degrees and so on. Okay, so we have this notion of orientation, and you can also have inclined edges and so on. Right? So you can think of a situation where you have an image and then right, you have something like this, and then let's say this is 0 and that is kind of say 255, and let's say in this case, just for simplicity, we can say that theta is probably 45 degrees or something. Okay, so you have a gx component and then you have a gy component. In the other upper two cases, you had one of them as 0, but it need not be. Right? So you can have something like this, right, where you have a theta, which is kind of pointing in the kind of say direction of the highest change of the say intensity. Right, in this case, it's going from 0 to say 255. And we will see there are certain detectors, right, edge detectors that actually make use of this information, orientation information, and most of them need the magnitude in any case. But there are some that may not need this, but they still they still can still function without them. But in general, right, whenever you talk about an edge pixel, you are talking about the magnitude at that point, right, magnitude of the edge of the the strength of the edge. So so when we say gradient, right, magnitude of the gradient, you are talking about relatively, you are talking about the strength of that kind of pixel. You are still at sort of a pixel level, right? We are still talking about what's happening at some x comma y, okay, and then it remains to be seen, right? I mean, how you then right, what kind of higher inferences can you make if you had many of them and so on, right. So, we are not yet there. So, that is one thing, right, that I wanted to mention. So, right, so I think you can even talk this, think of this as magnitude of g, whichever way you want to write it, and yeah, this I said. And of course, so the filter, right, I mean, I'll be a little loose, but yeah, but then, right, you should remember that suppose I say that, right, this is my filter, let's say, right, I put this as minus 1, minus 1, minus 1, 0, 0, 0, 1, 1, 1. Okay, this is one of the filters that you've already seen. And sometimes, right, people have what is called, a gain normalized filter, and also they'll have a scale factor here. Let's not worry about such simple things. These are called, gain normalized and so on, but that's just a matter of, adding some scale factor there. But what you have to perhaps keep in mind is that we always mean theta, right. Generally, the sort of say convention that we have is from 0 to 255, right, we will want to think of that as theta equal to 0. So, if you use a filter like this, right, and if you are actually doing a convolution, then you will flip it, right, and then right, when you kind of flip it, right, then this interpretation theta may turn out to be 180, right. So, you just make sure that you kind of adhere to this. So, in this case, it should perhaps be more meaningful to write it as 1 1 1 0 0 0 minus 1 minus 1 minus 1. So, that when you kind of flip it, right, 1 goes on the other side, and therefore, right, when you take the weighted average, if 255 is on that side, that will make it to be a positive number, and therefore, your theta turns out to be 0, right, that is all. So, that is something that is just a minor thing that you have to be wary about, otherwise you might say I am getting a theta that is of the opposite sign or something, right. Now, one of the things that we realize is that, when you take a gradient, right, typically we know that, that also increases the amount of noise, right, because we know that gradient itself is a kind of a differentiation operation, right. So, how much do you think a noise will go up by? See, for example, see if I had a case, right, where let's say I have an image GMN, okay, which is what I observe, okay, but then let's say this is some FMN at that. So, FMN is actually the ideal intensity that should have been there, but then due to some noise I get some n of m comma n. This is the noise, right, that is there, and let's say that this has some 0 mean. So, this is again a Gaussian, okay. So, this is let's say Gaussian with 0 mean and let's say variance sigma square, right, that is what it is. So, this noise, okay, is actually Gaussian. So, now if I take a difference operation, right, if I do a difference operation on this G, right, then intuitively we feel that differentiation we always say will amplify noise, this is something that we keep on saying, right. But can we kind of tell as to how much will be the increase? So, for example, right, so if I do something like G of m plus 1 minus G of, okay, now let us just take, right, one variable, okay, let us not kind of meddle with both, we can do that, right, there is no problem, but let us just take m minus 1, right. If I just make it to be 1D, let us just take a 1D case, right. What will happen? We will have like f of m plus 1 comma n plus n of m plus 1 comma n. So, a difference operation is this, right, that is what you will do as a kind of a discrete approximation, plus minus, then you have minus f of m minus 1 comma n minus n of m minus 1 comma n. Or in other words, right, we can think about this as f of m plus 1 comma n minus f of m minus 1 comma n, and then the noise component, right. So, after the right, differentiation operation, you have a new noise, right, which seems to, so after that, right, this you can think of the output noise component that you have, that has come out because of a differentiation operation, right, and therefore, if you compute the variance of this noise, what will that be? 2 sigma square, right. So, it will be actually 2 sigma square. So, it has 0 mean, and of course, right, this is all independent. So, therefore, right, you get actually 2 sigma square. That means the fact is, right, if you take a first derivative, right, you are already blowing up the, so the noise, right, that is kind of say coming in is actually higher than the noise that you started off with. That is the reason why we said that it is always a prudent thing to do first a smoothing, right, so that such small variations that are there, right, they could be sort of mitigated to some extent, and then right, and then you do a differentiation, right. So, the idea is to suppress noise with some kind of a smoothing operation, and that may come at the expense of some loss of information, right, because you will, when you smooth, right, it does not mean that it comes for free, but whatever it is, right. So, smoothing so that is why when you had a derivative of a Gaussian, see dog, there was another dog, what was that? A difference of Gaussian, yeah, you saved my life, okay. So, right, so it is like a difference of Gaussian, the other one is a derivative of Gaussian, right. So, these two are not the same. A difference of Gaussian is supposed to be a good approximation to the log, right. That is what I had mentioned now in one of the classes. But derivative of a Gaussian is also another way to take a difference, do a difference operation, where you first blur and then use a Gaussian and then you do a differencing operation. So, this is also another operator, by the way, right, a dog. This is a derivative of Gaussian. Okay, now let me just show you some examples, right. I mean, where okay, yeah. I mean, right, let's just go back and kind of revisit the log, Laplacian first, right. So, so what we had, right, at that time we had talked about a Laplacian. A Laplacian was what you do dou square f by dou x square plus dou square f by dou y square. That was a Laplacian, and the kernel was like 1 1 1 1 1 minus 4 in the middle, right, northwest east south, and then minus 4 in the middle. And so clearly that being a second derivative operator, it will introduce, right, even more noise, right. But suppose let's say right, let's kind of leave the noise aside. We realize that, yeah, right, it's going to be a problem because going for a second derivative will mean even more noise. But let us say, right, if you simply tried still doing something, now right, I'll just give you an image, okay, and let's say, right, it has these intensities. So just a toy example. Let's say that I've got two all 2's. Okay, need not be like this. Okay, no real image will look like this, but these are all toy examples. Let's say I've got, what is it, 8 8 8 8 8 8 8 8 8 8, and all of these, right, will so here also it's 8 8 8. Here on the left it's 2 2 2. Now suppose I took this Laplacian, right, which is 4 in the middle, and then what was it? I mean, did we have sign minus 4 in the middle or 4 in the middle? Which way did we 4 in the middle, and then we had minus 1 minus 1 minus 1 minus 1, right, zeros elsewhere, right. And therefore, if you apply this, right, what will be the output? So, if you do a Laplacian kernel, which means you will just do a convolution, then what will you find? Of course, in this case it's a symmetric operator. You flip it, nothing happens. What will be the output?
The 2 2 2 region, it will all be zeros.
It will all be zeros, but at the boundary, right. So when I am here, right, what do you have? I will have like 2 into 4 8, and then I have got like minus 2 minus 4 minus 6 minus 14. So minus 14 plus 8, that's like minus 6, right. So let's say right, so you got like minus 6 at this place, and then when you transition to 8, right, so it will be actually plus 6. Okay.
And
zeros elsewhere, 0 elsewhere, right. Now I said that a Laplacian gives you a sense for zero crossing, right, and zero crossing is the place where you can actually locate an edge. See, the point is, right, when you talk about an edge, it's not simply to identify the edge. It's also important to have just one response for an edge. Okay, what it means is, see, for example, right, I mean, see here, right, I would like only a single sort of, this one, a response, right. I should not find a thick edge there, because I see that there is only one edge and it's sharp, right. I mean, I should not get multiple kind of a response where I end up with actually a thick edge. I'm not saying it's happening here, but I'm saying that is something that you don't want. Two, what you also want is a localization, a good localization. That means I should know that the edge actually exists at that location. Now here, where does the edge exist? Between the two. So that means that the zero crossing is happening somewhere between the left and the kind of say right pixel, right. So such a thing is called a subpixel localization, right, because it's not happening at the place where you have the intensity, where you have a pixel location on your spatial grid, right. So it's happening like, for example, you have one pixel here, and then right in between it's going through, right, or it's changing its sign, the second derivative, and therefore your actual edge is located somewhere here. Okay. Now in this case, right, it is, I mean, I just took a toy example where it is minus 6 and 6, right, it's kind of an ideal case. If I had something like, let's say, what is it, so suppose I said that, right, I have minus 6 here, and suppose I have 3 here, suppose, right, the intensities turned out to be like that, where will the edge be?
Somewhere in between.
There. I know, somewhere in between, because it has crossed over, no? But why and how? But I want to know where. Okay, now, yeah, I know that, right, it's not a straightforward answer. So now what is typically done is you have to do some kind of an interpolation. Huh? Yeah, right. So you have to do some kind of an interpolation to know. But if I said that the simplest I want to do is a kind of a linear interpolation. Suppose I said I want to do a linear interpolation. How would I do this now? That's the simplest thing you can do, right? Just take a linear interpolation and tell where the location is. Where is the location now?
0.
Where it should be 2/3, right? So suppose I say that, right, a is 0, okay, and that location happens, let's say, right, it's a delta away from, let's say, -6, okay. Now for example, right, what is a now? If I did a linear interpolation, how would I write a in terms of -6 and 3? I have to write a in terms of these two, no? So how would I write it? I mean, I'm not even saying a is 0 now. Somewhere I have an a somewhere. I want to express it as, in terms of -6 and 3, right? We'll then equate a to 0 because that's the 0 crossing. But in general, let's put a somewhere and it's kind of delta away from
When delta is 0, it is -6 and delta.
So what should, so I'm just asking, what is that expression then? Yeah, you're telling me 1 minus delta -6 plus delta into 3, right? Delta times 3.
It's 9 delta minus 6.
So it is what is it? So a is -6 plus 9 delta, or 9 delta is 6, therefore delta is 2 by 3, as he kind of rightly said, and that also matches with what you said. It will come to the closer to 3 because half is like in between, right? So it will come. So it means that so actually, right, in reality you could do that. I mean, right. So when people do this many times, right, when you want subpixel accuracy, or the simplest thing that you can do is, you just go with some kind of this one, a convention that let's say if it is going from -6 to 6, I'll take -6 to be my edge. That is also possible. But you can also do subpixel, right, but it will require more information. But right, that's also commonly done. Okay, so that's what we mean by pixel localization. That means we have to know where exactly the edge is occurring. The problem with Laplacian, right, as we know, the good thing is that it is telling you 0 crossing, right, which means that there is actually very good information about where the edge lies. And you can imagine, right, this is going to be very useful if you have actually a smooth transition, like we showed the other day, right. You have a smooth transition. If you take a kind of a first derivative, right, then of course you know that where the extrema is, that's an indication. But when you take a second derivative, the 0 crossing, right, automatically tells you, right, where it is. But then if you just took all the 0 crossings, right, that are there, and if you declared all of them as edges, right, then it's not actually a good idea, because then you will have an image, right, that just has too many things out there, because you can have extraneous extrema and all, right, that will all enter.